Hello and welcome back. We're going to talk about moment inertia. Moment inertia, what is it? As they say, it's a second area about a shape, but moment inertia represents the cross-section of an element. Later on, if you're in civil engineer, you're going to go ahead and learn about beam and column. And beam and column, we're going to have stresses in them. And these stresses, one of the stresses, for example, is fluctual stress or bending stress, which in the formula of bending stress we use moment inertia. Just let me show you something. Assuming this is a beam right here, and this beam is bending, down the center of the beam is what we call neutral axis. And then you have compression in here and tension down here. And this distance we call C. And then you have a stress. Your bending stress or fluctual stress, sometimes it's sigma, sometimes they say FAB. That's basically MC over I, bending moment. You will learn that later on what bending moment is. I mean, on top of the beam, where you use a weight on it, the maximum compression is right there, and then the maximum tension is at the bottom. As you get closer to the neutral axis, the stress is zero. And if you look at the cross section of this stress, it's going to look like something like this. This will be compression, and this will be tension. It's going to come in like that. You have a maximum compression down there, maximum tension down here, and in the middle you have a zero. And this I, moment inertia, represents the ability of the cross section to resist bending stress or in column. If you look at this, say this is a beam. If I have it like this, it bends easier. But if I go ahead and bend it like this, put load on it, the bending resistance is going to be greater because the moment inertia is greater based on the height, and makes a big difference with the cross section, whether you look at the cross section this way or this way, as you can see from here in this example. So now, moment inertia, the equation for a rectangular shape, as you can see on the board, for different type of shape, for rectangular shape is 1/12 bh cubed. However, if you got compounded or you have multiple shapes, then you can use 1/12 bh cubed plus AD squared. I explain that as we do an example in a minute. Let me erase this. So now we have this shape, and we want to go ahead and find the moment inertia of this shape. First, I'd like to know what is the center of gravity or neutral axis of this cross section of this beam is. But before we do this, I'm going to divide this to three different sections. Let's call this as shape number 1, and this will be shape number 2, and this one will be shape number 3. And so now I'm going to go ahead and on a shape number 1, I'm going to calculate, as I set up a chart like this one to make it easier as we go along. The equation for it is this. We can go ahead and do individually like this, but this will explain a little bit easier step by step. So I'm going to go to section 1, and then section 1, I'm going to find out the area of number 1. It's going to be A1 right here, and that's basically 6 times 1, which is 6 inch square. And I'm going to come in here, put 6 right there. Now remember, when we do these cross-sectional, you can go ahead and establish your x and y axis. I know the y is down the center here, and the x is in the middle. But I'm going to measure everything from this down bottom here. I'm going to call this my reference point right here. I'm going to put an x in there. So I'm going to measure everything from here up. Now I'm looking for y. Where is the y? Is the center of my shape. If I just have this shape right here, and a y is the center right here. So that's my y bar, which is basically from here to there. It's in the middle of a rectangular. If I'm looking for x bar, obviously it's from here to there. But we're looking for y bar, which is the center of this shape. And center of this shape, it's going to be right here. This is 1 inch, therefore it's going to be ½ inch. So I'm going to have 0.5 right there. And A times y basically is the area times y. 6 times 0.5, and that's a 3 inch square. All right, so let's leave it like here. We'll come back, fill the other one up. I'm going to go to shape number 2. In shape number 2, it's this one right here. The area of number 2, it's going to be 1 inch times 12, which is equal 12. and we know the area is 12 right here. Now, what is the y bar? Y bar is the center. My y bar is the center of this shape right here, which let's say this is a 12 inch, it's about 6 inch right here, and that's the center of it. But what is the y bar compared to our reference point right here? If it's from 6 to here, then it's going to be 7 to the bottom. And that's why we say y bar is 7. And then 8 times 12, 7 times 12, it's coming out to be 84. Great. So now we have that, and we're going to go to the shape number 3. And shape number 3, it's basically 12 times 1, same thing. It's going to be 12 inch square. And I'm going to say, all right, shape number 3, 12 inch. But what is my y bar? My y bar is, again, it's in the center right here, which is half an inch from the top right here. So half inch from there plus 12 plus 1 makes it 13.5. 13.5. And that should come out to 162. And I'm going to go ahead and put a summation in here, sum it up. And basically the summation of the area is going to come out to 12 and 12 is 24, 6 is 30. And let's do the AY. AY comes out to 249. All right. And my neutral axis, y bar is equal summation of A times y divided by summation of area. And that's going to be 249 divided by 30. Which is going to come out to 8.3 inch. So what does it mean? It means my neutral axis from here, neutral axis is going to be someplace like this, and at distance is going to be 8.3 inches. That we're going to find out, continue with D. Now D is a distance between the center of your shape that you're looking at and the your center of gravity or your neutral axis. So for shape 1, the D is this distance. If this center is right here, this distance between this center and that one. So D1 basically is going to come out to, this is we said this was 8.3 inches, minus 0.5, and that comes out to 7.8. So we have 7.8 right here, and A times D squared comes out to 365. So let's go ahead and find D2. D2 is center of this shape to this neutral axis. The center of this shape is, we said, it was 7. So it's 8.3 minus 7, which is 1.3. So I got 1.3 right there. And the next one is that D3, the distance between right here and here. Well, we know from here to the bottom here is 13.5. So 13.5 minus 8.3, 5.2. So this one is here is 5.2. And going back doing AD squared for this one, if I can multiply this by square this by AD squared, comes out to 20.3. And this one comes out to 324.5. Now, what I want to calculate while I'm here, the moment inertia of each individual shape. So I of shape 1, which right here is 112 BH cubed, which is equal to 112. Our B is a 6-inch, and our A is only 1 inch, 1 by power 3, and that comes out to 0.5. So this is a 0.5. Then I'm going to do the same thing for the second shape, the moment inertia for the second shape, just the shape itself, and same thing, and is equal to 112. Our B is 1 inch, and our H is 12-inch cube, and that give me that comes out 144. So I have 144 here. I'll continue to do the same thing. IO3, that is 112. B is 12, and H is 1 cube, and that comes out to 1 inch. These are inch by power 4, by the way. Inch by power 4, so this become 1. Now we filled out everything. We have that. Let me erase this. Said the moment inertia for the entire shape is Ix is equal summation of all of that. So I'm going to say Ix is equal summation of all of the IO plus AD squared. Let's put a parenthesis around it. And our Ix comes out to, we already have used the table. A lot of times it's easier to use the Excel. Put this in Excel, you have it, and next time it makes it easier because you already set the formula for it. So now I have IO, sum this all, if I sum this is 145.5, and this came out to be 709.8. So I have 145.5 plus 709.8, and the whole thing comes out 855 inch by power 4. Now, that's why moment inertia is so important, this number, what this number comes out to. If this beam was taller, this number comes out bigger, and that means the resistance of the cross-section material have a bigger resistance toward bending, buckling, and all that stuff, and it makes a big deal. And again, if you tip this over, try to load it, it's not going to work. It's going to collapse a lot quicker because your moment inertia is going to be a lot smaller. I hope this was useful, and if it is, please give it a thumbs up.